Good morning, everybody. This is Nicholas Zavaras, and we continue the lectures on statistical computing and machine learning. So the lecture today is a continuation of our earlier lecture on accept-reject sampling methods or rejection sampling methods. So let's see the type of topics we will cover in the lectures today. So we will review the accept-reject algorithm. I'll give you an example on how to apply it for sampling from the gamma distribution. We will talk alternative interpretations and algorithms for the accept-reject sampling, including what's called the Moxture method. Discuss a little bit about the limitations of this method in high dimensions. And also I will give you an idea on how this relates with sampling from the posterior distribution in a Bayesian setting. We will also talk about how to generalize this method so that the proposal distribution is not something you have to worry on selecting it arbitrarily on your own. So we will talk about these envelope rejection methods in coming up with a proposal distribution as an envelope to the actual target distribution. And then I'm going to finish with another accept-reject method that goes with the name Monahan's accept-reject method. Basically, I want lots of these new methods today to be used as examples that somehow allow you, through this accept-reject idea, to sample in an algorithm that looks complicated, but at the end implements implicitly the same ingredients that we have seen up to now with these rejection sampling algorithms. Okay, so the topics today will reinforce the following goals. We will need to learn how to use and all the ingredients of the accept-reject algorithm. We will learn about the envelope rejection method and the Monahan's accept-reject method. So let's go and review some of the things we discussed in our last lecture. So remember, there is a target distribution pi of x. This target distribution is only available to us up to a normalizing constant. So pi star is the distribution without a normalization constant. And the key idea of the rejection sampling is that there is a proposal distribution that is easier to sample from, and we call the proposal distribution Q, and the anormalized part of it, we call it Q star. Okay? Now, to make these methods to work, Q needs to dominate pi, and we define what that means. It means that this maximum value of pi star over Q star over all possible values of x has to be finite, and in practical sense you can think of pi star over Q star being less than some constant. Okay, so we need to establish that this inequality that Q dominates pi to make these methods to work. Now, in principle, as we discussed in the last lecture, this means that the tails of Q star have to be thicker than the tails of pi star, and in places of the support space where pi star is positive, Q star has to be positive as well. Okay, so that's the accept-reject idea, and here is the algorithm. So let me put up all the ingredients of this algorithm. So we're going to find first an M prime that satisfies this equation that indicates that Q dominates pi star. And the algorithm proceeds as follows. We sample Y from the proposal distribution. We sample U from the uniform distribution from 0 to 1. And then we compute the acceptance probability that is defined as pi star of Y divided by M star of Q star of Y. And so if the U we selected from the uniform distribution is less than this quantity, we accept Y and we set X equal to Y, and that X then is a sample from the target distribution pi of X. So again, we sample from QY, we sample U from the uniform distribution, and we accept Y with a probability pi star of y divided by m star of q star of y. And that's how we create samples from our target distribution pi of x. Now, we discussed that if m is too large, basically we will rarely accept any samples, so the algorithm will become very inefficient. So you can see pictorially again the same algorithm, and so this is the y that you sample. Then you sample u from the uniform distribution, so you can see u times m prime times q star of y has to be less than pi star of y. So in this location y that you sample, if you compute m star q star of y times u, which is represented here with this point has to be below pi star of y at this particular location y for the sample y to be accepted. So this is the acceptance then region for that location y. So if this dot point is inside that region, we accept, otherwise in that region we reject. And we emphasize again, and you will see today in the lecture, that these distributions, both pi and q, have to be known up to their normalizing constants, and I denote those distributions as pi star and q star. Just pay attention when you look at different textbooks. You may not see the constant m because the way they operate is sometimes they use one of the distributions to be already normalized, but in our case we keep the notation as general as possible. Okay, so one of the things that we proved was that so we know we sampled from this proposal distribution, and we computed the probability of acceptance, and that probability of acceptance was nothing else but the normalization of pi star divided by m prime times the normalization of q star. Okay, so this is the probability that a proposal will be accepted. Okay, and we mentioned that in expectation, this probability, one of the over the probability of acceptance, effectively gives us in average how many samples we have to take from the proposal distribution before one sample is accepted. And the way we computed this is we recognize that this probability of the kth proposal being accepted follows a geometric sequence with probability gamma of acceptance that you see here, and for the geometric distribution, the average of k is 1 over the probability, so 1 over gamma, so 1 over this factor that you see here defines in average how many times we need to sample before we accept a sample. But again, remember this probability of acceptance, because you can see immediately that if m prime is very large, so if you do a very lousy job in bounding pi star with q star, then effectively this probability of acceptance would be very low, so the algorithm would be extremely inefficient. All right, so let's do one example. You remember we discussed about using the transformation equations in sampling from the gamma distribution, but the parameters of the gamma distribution we used were integers, so that was not very general. So let's try to have to use this general gamma distribution that you see here, and let's say we want to sample for arbitrary values of alpha and lambda. We want to sample from this gamma distribution. Okay. Now, if you remember, if xi are IID samples from the exponential distribution with parameter lambda, then y, that is x1 plus x2 plus xk, etc., is a sample from the gamma distribution, but then you notice this parameter here has to be an integer, right, the way that we have defined it, so k has to be an integer. If alpha or a is not an integer, we will not be able to apply this transformation equation that we saw in the earlier lecture. So what can we do for non-integer a? The idea is for non-integer a, we can use as a proposal this gamma distribution, where this parameter here becomes an integer by taking the integer part of a. That's what this notation indicates here. So that's the integer part of a. And then the parameter lambda that I take for the proposal distribution becomes lambda minus 1. Now, why is that? Because effectively you can see that this particular q can dominate pi with some constant. So if we take the ratio of pi over q, so you substitute your pi, okay, that's what we have here, and you substitute the proposal distribution, which is another gamma with an integer k and lambda minus 1 here. This is what we get, okay? And now we need to figure out if we can bound this ratio for all x's with some number m. So we need to compute the maximum of this over x. And actually, if you do the calculation, you will find that this ratio receives its maximum value for the location x that is given by a minus the integer part of a. Again, this is bounded by x being a minus the integer part of a. So in that case, the constant m that we can bound this ratio of pi over q is nothing else but the ratio of the two gamma distributions for x being a minus the integer part of a. And this is what I have here, right? This is my proposal distribution evaluated at a minus the integer part of a, and this is my target distribution evaluated at a minus the integer part of a. And again, the target distribution has general parameters a and lambda. The proposal distribution has parameters the integer part of a and lambda minus 1. So we have a proposal distribution, we have the constant m, so we are basically ready to start doing the accept-reject algorithm. But you know, if you look at the schematic here on how m times q dominates pi, you will notice that this methodology is not ideal because effectively this constant m, the way we have it, is rather large, and that you know, points basically to the fact that this algorithm may not be very effective. So here is an alternative way to sample from the gamma distribution using again the accept-reject methodology, but using a different proposal distribution. Okay, so the previous methodology was actually given in Kevin Murphy's machine learning book. So what I will describe on this slide, it goes back to a very old paper coming out of Stanford in 1974 that is actually going to use as proposal distribution for the gamma the Cauchy distribution that, as you remember, has fat tails. So here is my target distribution, and for simplification I take here lambda to be equal to 1. It's very easy to put any lambda there, but I'm going to take lambda equal to 1. So alpha is arbitrary and you know, non-integer, and alpha is greater than 1 for my gamma distribution. So I take this to be the proposal distribution, and the reason I am taking the Cauchy to be the proposal distribution is because we will see that it dominates the gamma distribution, but it's very simple also to sample from the Cauchy distribution, because the Cauchy distribution has a very nice CDF that you see here, and this CDF is very easy to invert. So you can you can sample the Cauchy distribution with the inversion method, where you sample a uniform random variable from 0 to 1, then you invert the Cauchy distribution, and that will give you immediately a sample from the Cauchy distribution. And then you can use that sample to follow up the accept-reject algorithm and see if you will accept it or reject it, exactly as we discussed earlier. So let me see some of the details. So the most important thing is to show that the target distribution is dominated by the Cauchy distribution, and this is what this particular paper showed in 1974, is the following inequality. I apologize again for using slightly different notation. Instead of calling this pi, we call it f, but the reason for that is I try to stick with the original notation of the references used, so that way we don't do any mistakes. But certainly when you read the slides, it will be self-explanatory as exactly to what the different symbols mean. So this is my target distribution, and the inequality that they proved, and the proof is very simple, is given in this link if you want to read it. It shows that this pi is, this f of x distribution is less than this, and you notice there is some constants, okay? Some constants, let's forget 1 over gamma a, because it's the same in both left and right hand sides, but also you can recognize 1 over 1 plus this square divided by 2a minus 1, which actually reminds you the Cauchy distribution. So actually you can write this right hand side, adding a few, a normalization constant for the Cauchy distribution. You can immediately see that your target gamma distribution is bounded basically by Q star, where Q star in our case is the anormalized Cauchy distribution. So in the notation that I used in the lecture earlier, pi star is basically x a to minus 1 e to the minus x. That's the anormalized part of the target distribution. Q star is the anormalized part of the Cauchy proposal distribution, which is 1 over the denominator here. This is what I have. And the constant that bounds pi star being less than m star times q star is nothing else but e to the minus a minus 1 to a minus 1, because these things are cancelled out. So this is my pi star, and it is bounded by this constant times q star, so m star is given like that. Okay, and you can actually show that if you compute the normalization factor of q star and the normalization for pi star, and this is, I have them here explicitly, you can show that the number of trials that you have to go through before you accept the sample from the proposed distribution is given by this long expression, which is really nothing else but this constant m star divided by gamma of a times this normalization coming from the Cauchy distribution. Okay, so in the accept-reject distribution, in the accept-reject algorithm, what we will need is we will need basically to evaluate q star at different x's. We will need to evaluate pi star at different x's, and we will need to use pi star m star to decide if a sample is going to be accepted or not. And this is what I am going to show you in this very short algorithm that is summarized with those 4 steps. I am not going to go through the details, but I strongly advise you to verify that the equations that we saw in the previous slide, they coincide literally with what you see in these 4 steps of the algorithm here. So you remember the first thing we need to do is we need to sample from the Cauchy distribution. And to sample from the Cauchy distribution, we're going to use the inversion method. So you sample u from 0 to 1, and you use the inverse CDF of the Cauchy distribution, and that eventually gives you a sample from the Cauchy distribution. Then you will either accept or reject this in our accept-reject algorithm. So you are going to sample again from the uniform distribution from 0 to 1, and if u prime tends to be bigger than that, then you will reject, and the algorithm will be repeated. Otherwise, you accept the sample X. Again, this equation is written as if you were to program it, but please do verify that with the definitions that you see on step 1, exactly this is going to give you the acceptance, the acceptance probability for the proposal. Now, it turns out that this bound that we have now of the gamma distribution with the Cauchy distribution is way, way better than what we saw earlier using the methodology from this machine learning book of Murphy. So you can see here, this is my gamma distribution, and this red is basically the bound that I can get with the Cauchy proposal distribution. Again, as I mentioned, the expected number of trials is given by 1 over gamma, is given by this expression, and you can actually verify that this number can decrease from 3.14 when alpha equal to 1 to 1.77 as alpha goes to infinity. Okay, so this gives you about a rough idea of how many samples you have to take in average before you accept 1. All right. Now let's discuss a little bit about alternative methodologies for the this accept-reject algorithm. So you notice that in the algorithm up to now, we sample Y and then we sample U, right? And generally, that doesn't have to be the case, okay? Now, more importantly, what I want to tell you today is I want to tell you that you can come up with rejection sampling algorithms that somehow introduce minimal information about the conditions for acceptance or rejection. And so let me proceed, and I'm going to define an algorithm introduced by Beskos et al. That applies the accept-reject algorithm as follows. Okay, so let's say that you're generating samples, sequence of samples, yn, in. I'm going to explain why is sample similar to what we were sampling before, and this I are indicator variables. So I'm going to be generating a sequence for n equal 1, n equal to 2, etc. This sequence, each of them will be, each sample will be IID, all right? So Y takes values in this space X, and I is an indicator function that takes values 0 to 1, and Y1 comes from some proposal distribution Q, okay? So this is what we have up to now, and the only condition that I'm going to introduce in this algorithm is the following condition. I want the probability of the indicator function I1 being equal to 1, given that Y1 equal to Y, to be pi star over C times Q star. And again, I am using the exact notation coming from this paper, so you can interpret this C being the constant M that we had in our generic notation earlier in the lecture today. So you notice this condition is not extremely strong, right? It doesn't say too much. It says you're sampling Y1 from a proposal distribution, and this is the constraint that you have, okay? Now, we are looking for something in this algorithm that says what samples are going to be accepted and be samples from a target distribution, and our target distribution, of course, here is as before, it's this pi star. So here is what the algorithm says. You're going to define tau to be the minimum of the i's from all of these potential i's for which the indicator function is equal to 1. So you find, in this sequence of y1, i1, y2, i2, y3, i3, you find the I for which I1 equal to 1, and you find the minimum of those i's, and we call that tau. Then the y at that tau, it's a sample from the target distribution. All right, the y from that tau is a sample from the target distribution. So actually you can appreciate the fact here that somehow this algorithm introduces literally minimal information on the acceptance or rejection of this proposal element y, so we don't really have an acceptance probability the way that we had before, and beyond this constraint, right, everything else sort of is completely left up to you. Okay, so actually the scheme does not assume what sequence you sample y and I. They're arbitrary, and again the only constraint that you have is this one, and it doesn't even tell you how the construction of this indicator function I is going to happen. So you are left basically with lots of choices. Now this algorithm is very cryptic, right? So if I give it to you as a homework and I say sample the sequence of y and I such that y1 comes from the target distribution, and this conditional probability of i1 being 1 given y1 being 1 equal to this, and then select tau to be the minimum I for which I subscript I equal to 1, then it will be hard for you to believe that the y sample for that tau is actually a sample from the target distribution. So let me highlight the proof, okay? And the proof again is given in the paper that you see on the bottom of this slide. So we're going to do this proof in 2 steps, okay? So first, let me compute the probability that I1 equal to 1. All right, so this is the probability of I1 equal to 1. So because I am given the probability of I1 given 1, given that I have capital Y 1 equal to Y, I am going to write this using the sum and product rules of probability as such, where y, of course, is a sample from the proposal distribution Q of y. So I am substituting this conditional probability, as you see here, with this, and let's see what I get, right? I have Q over Q star, so literally what this will give you the normalization factor for this integral of Q star over the support space S, and then on the numerator you basically have this this normalization factor pi star. So effectively what we get is we get the probability of acceptance that we had seen in the earlier part of these rejection sampling algorithms. So the probability of I1 equal to 1 is given but by what we call gamma before. All right, step 2. That would be a little bit more complicated. So let's compute the probability. So you remember the algorithm said that if you select tau to be the minimum of the i's for which capital I subscript I equal to 1. So let's compute the probability then of that y tau to be in some measurable space f. Okay? So I am going to write this using this sum and product rules of probability again as the joint probability of y tau being in f and I1 equal to 1, and then the probability of y tau being in f and I1 equal to 0, and then I use the product rule on the second term. Okay? All right, so let's, obviously the objective here will be to prove that this is actually the probability under the target distribution the probability basically of f under the target distribution, right? That's what we want to prove. So let's see if, how we can actually come up with this proof. So the first thing I'm going to use is what was given in the description of the problem, and the algorithm says that this sequence of yn in for n equal 1, 2, 3 is an IID sequence, and then of course remember the definition of tau being the minimum of I such that I subscript I equal to 1. Okay, so let's see what simplifications I have done. The first thing I notice here, this term has been written simply as the probability of y tau being in f. Why is that? Well, because I1 and y tau, all right, are independent. Okay, so so again, because this, y tau and I1 are independent, okay, this is simply the probability of y tau being in f. Now, let's do a calculation now of the first term. So on the first term, I can do again this product rule of probability, but I can write it as the conditional of I1 being equal to 1, given that y1 equal to y times cube y dy. And now you may ask me, what's going on here? Why suddenly from y tau belonging in f, I went to y1 equal to y? Remember that how is tau being defined? Tau is the minimum of I such that I subscript I equal to 1. And because I1 equal to 1, here I do have in the first term, I have y1 being in f. Okay, so this integral that you see here, all right, this integral over f, effectively it's equal to this probability that you see here, because tau has to be equal to 1. Okay? Alright, so let's simplify the calculations a little bit more. So this conditional probability that you see on the first term here on the right hand side, it is given in the problem statement, in the algorithm statement. It's pi star divided by c q star times cube y, and that's an integral in this measurable space f. And then the second term remains as is. And then what I have is, again, this left hand side equal. So let's simplify what's going on the right hand side. So here what you notice, you have q. So you can write q as q star divided by the normalization factor of q. Q star and q star will cancel, so you get the normalization factor of q star. And then here you have pi star, and pi star, you can write it as pi of y times the normalization factor of pi. So that's the normalization factor of pi times pi. And then what you have is, you have this integral, which is the probability of f. All right? So again, please just use the definition of the normalization constants for pi and q, and then effectively the first term becomes what you see here. Now, notice again that this is gamma, right? This is the same that we introduced earlier on step 1, so this is gamma. So I can move this term to the left hand side, and eventually you can immediately see by rearrangement of terms that the probability of pi for yt to belong to f is pi of f. So effectively we have proved that this sample y of tau, it is actually a sample from the target distribution. So what is amazing with this algorithm, right, is that somehow, if I can go back to this main idea, the algorithm has relaxed a lot of the conditions of the rejection sampling algorithm. It doesn't tell us much about how to sample I or what algorithm is going to be used to produce I. So there is lots of freedom on what you do with that. It basically introduces only one constraint, and then based on that constraint and the fact that we take these samples Y and I to be IID, it says define tau to be the minimum of I such that capital I subscript I equal to 1, and then we just prove that Y subscript tau is a sample from the target distribution pi. So effectively we have been able to construct these general conditions for the acceptance rejection of of the proposal sample Y with using minimal information, okay, and leaving basically a lot of flexibility as to how these various how, for example, I is being constructed in this algorithm. Okay, so that's this alternative rejection sampling algorithm coming from this paper of Beskos and Roberts back in 2005. You can consult the paper for extensions of what you see on this slide if you are interested. All right, so now what I want to do is I want to show you the similarity of this accept-reject algorithm with actually sampling from a mixture distribution. So I remind you that in the standard accept-reject algorithm, right, we draw a sample from the proposal distribution, and maybe that sample is not accepted, then we draw again another sample, and then another sample until that sample is accepted. And I already had mentioned that this is very similar to actually sampling from the geometric distribution. But now what I want you to interpret this is as actually sampling from a mixture distribution where you have this infinite, a mixture of infinite components with probabilities that they're coming from this geometric distribution that you see here, where pi is nothing else but the probability of acceptance that we have seen many times in this lecture today. So the algorithm tells you that the accept-reject algorithm is similar to sampling actually a component from that mixture, a component I, and then once you sample that component, then you can go and sample from the underlying pi subscript I of x. But you notice in the way that we define this mixture here, all the pi i's are equal to the target distribution pi of x. All right, so all the pi i's are equal to the target distribution pi of x. Now, when you look this equivalence of this rejection sampling with sampling from a mixture, you may get the impression that effectively you are going to find some fast way to sample from the geometric distribution with this probability p, but in reality the way that you will implement this algorithm is exactly as we have done already. So you sample from the proposal distribution, you accept or reject, then if you reject, you sample again, you accept or reject, if you reject, you continue sampling again until you find a sample that is being accepted. So basically you're not going to sample from the geometric distribution, but you will actually be testing if I equal to 1 or if I equal to 2, what sample basically is going to be accepted, okay, using the standard algorithm that we have seen up to now. Now you may say, what is the merit then of this geometric distribution and using this mixture model where we use these probabilities to be the probabilities that we will accept at trial I, and then we take all the mixture pi I distributions to be the same, equal to pi of x. So what's the merit of that? Well, the merit of that is this mixture understanding can lead to new type of algorithms, And if you're interested to see some of these algorithms, my advice would be to look at this significant paper from 1982 that introduces some of these algorithms. So for now, let me just demonstrate again the accept-reject algorithm with this interpretation of sampling I from this geometric distribution, and then effectively once we have I, we sample from pi I of x, which is equal to pi of x. So let's take a target distribution to be a truncated Cauchy distribution that you see here. That's pi and pi star are the same, that it's normalized. I am going to take as a proposed distribution to be, as you can see here, it's a normalized proposed distribution, right? But I use a normalized version of it, Q star. So if you compute the maximum of pi star over Q star, it turns out to be 1. And the probability of acceptance here, if you compute the normalization terms and you plug in m equal to 1, it comes to be pi over 4. Okay? Basically, you're going to get a normalization factor from here being 4 over pi. So the normalization factor of this is 1, so you get pi over 4. So the accept-reject algorithm looks exactly the way that we have seen it up to now, so I'm not going to iterate. Not to get confused here, our proposed distribution is a uniform distribution from -1 to 1. So we're going to generate a sample from the proposal distribution, and then we're going to generate a sample from the uniform distribution 0 to 1. That's what we will use to figure out if we accept or reject the proposal. And then you notice if you compute pi star divided by Q star divided by m, well, actually you get 1 over 1 plus x squared. So if u is less than 1 plus x squared, you accept x. Otherwise, basically, you have to sample again from the proposal distribution and repeat the algorithm. So nothing new up to now, right? But if you see the mixture interpretation of this algorithm, the mixture is going to look like this: pi I times pi of x, where pi I is nothing else but the probability that the algorithm basically will be executed and will return an accepted sample at the ith step. Okay, so this is the number of times that steps 1 and 2 that you see in the algorithm are executed. This is how many times we're going through the algorithm before a sample is accepted. That's this probability pi I that you see here. It's nothing else but this probability of acceptance pi over 4 times the probability of rejecting for I minus 1 times, so 1 minus pi over 4 to the power I minus 1. Okay, so remember again, we use here that pi I is the same pi for all I, and I emphasize something interesting. When you implement a mixture algorithm, right, usually you make use of the I that you sample from the mixture components, but here that I is never being used. Okay? Because in principle, the only thing that you need is you need that sample X, and that sample X has already been computed as part of the accept-reject algorithm in the steps 1 and 2 that you see on this slide. All right, so that's the mixture interpretation. So let me continue. I want to emphasize with this slide that you don't really need to know the normalization constants, right? That's why I'm taking this effort in the notation to use as much as I can distributions that they are not normalized. So let's say that my target distribution, pi, is given by e to the minus x squared over 2 times m of x, where m of x is less or equal to some m. So I'm going to use the normalized part, pi star of pi. I'm taking a proposed distribution here to be normalized to start with, so that's a standard Gaussian, okay? And if you do your calculations, you can see that the constant m prime that we use to define how q dominates pi is nothing else but square root of 2 pi times m, all right? So you're going to get square root of 2 pi times m, all right? And the proposal that a sample will be accepted is basically the normalization of constant for pi divided by m prime divided by the normalization constant of q, which is 1. Okay? So let me repeat this now by omitting the normalization constant on q. So I'm going to use q star to be simply e to the minus x squared over 2. So if you repeat the calculations, it turns out first that pi star over q star is less or equal to m. That's that m. And the probability of acceptance, if you compute the normalization factors and you put the value of m there, it turns out to be identical as in the first case. So bottom line is, it doesn't really matter here if you use the q itself that is normalized, or you use the normalized part of q that is q star. So you do get exactly the same results with the same acceptance probability. Let me say a few words about the Bayesian setting, right? Because most of our course has been on Bayesian analysis, and even talking about Monte Carlo methods, you know, we motivated the need for Monte Carlo through Bayesian analysis. So let's say that we have a Bayesian model, all right? So there is a likelihood x is, let's say, observations with some parameters theta. Obviously here there is a typo that I will correct. That's the prior pi of theta. And we produce a posterior that looks like this. Okay? So the normalized posterior, it is basically your likelihood times your prior, right? This is what I have here. And let's say that we want to use the accept-reject algorithm to sample from the this posterior. Again, do not confuse x with theta. Now we are looking, our distribution is a distribution on theta, okay? So x is a measurement, right? So our distribution is a distribution on theta. Here is the idea. We're going to use as a proposed distribution to be the prior, and just to make life easy here, I'm going to take that the prior is normalized. It's a proper prior. So if you compute the ratio pi star over q star, all right, pi star is equal to that. If you divide by q, which is pi, you do get the likelihood, and you want to find the maximum of that likelihood for all possible values of theta. And you know, we have seen this thousands of times in this course. That is nothing else basically but the likelihood computed at the MLE estimate, by definition of the MLE, okay? So M turns out to be the likelihood computed at the MLE estimate. That's very nice. So you can actually go and apply your accept-reject algorithm directly for this problem, and the probability of acceptance, if you use our formula here, the normalization factors for pi star, q star, and m. So this will give you the normalization factor for the posterior, okay? This is the normalization factor for the prior that I take it to be already normalized, so that's 1. And so this is what I have, where m again is the likelihood defined for the MLE estimate of theta. So you can apply again the accept-reject algorithm for sampling from the posterior, where the proposed distribution is your prior, and m is defined to be your likelihood evaluated at the MLE estimate of the parameters. Okay, you know, like many things that we're discussing in our course, right? Everything has limitations, and the accept-reject sampling algorithm really it's not useful in high dimensions. And I'm going to demonstrate this with sort of a standard but trivial example, where we want to sample from this multivariate Gaussian distribution. Okay, so I'm taking this N0i multivariate Gaussian in d dimensions, and I'm going to use as a proposed distribution also Gaussian, but now with equivariance sigma square I, where sigma is greater than 1. Okay, so this actually proposed distribution will work. It's appropriate for this problem, but so if you compute to see, if we try to compute how Q dominates pi, and you compute the ratio pi star over Q star, what you're going to get from this, you're going to get sigma to a power d against the dimensionality of my multivariate Gaussian, and then on the exponents I'm going to get e to the minus this plus that, and because sigma is greater than 1, this here is positive, so this whole e to the minus, this positive number is less or equal to 1, so we can see that pi star over Q star is bounded by sigma to a power d, okay, where d again is the dimensionality of the problem. Now, if you look at the probability of acceptance, remember that is the normalization factor of my target distribution divided by m divided by the normalization factor of my proposal distribution. The proposal distribution in this case is already normalized. The target distribution is already normalized, so what you get is you get 1 over m. M is sigma to a power d. Sigma is greater than 1, so as d goes to infinity, so as the dimensionality of the problem increases, you can see that the probability of acceptance becomes 0. So effectively, if you try to implement these accept-reject algorithms in high dimensions, what you see is in practice you will never accept any of the samples because the probability of acceptance goes to 0. Okay, so that's a significant limitation of these algorithms in high dimensions. Okay, let's keep moving, and so we up to now we talk about the inversion method, inverting the CDF to do sampling from simple univariate mostly distributions. Inverting the CDF, of course, requires that you know the CDF, and then we talked about the rejection sampling that brings many new interesting ideas. The ideas are, you don't sample from the target, you sample from another easier distribution. That's the proposed distribution. Then the idea was the samples are not always accepted, there is an acceptance probability. So those are two ideas that we will see coming up in many more algorithms in follow-up lectures. Okay, the question that now I need to address is, can we remove the user of this rejection sampling algorithm from the need to have to come up with his own Q star that dominates pi star? So can we construct Q star in one way or another in some automatic fashion? And the answer is yes. There is a methodology that goes with the name Envelop rejection method, and I'm going to try to discuss this methodology in steps, okay, so that things can become clear. So let me start by bounding the target unnormalized distribution pi star not only from above the way we have seen it in the rejection sampling algorithms, but from below with some distribution Q star with subscript L to remind me that that's a lower bound. Okay, so let's assume that pi star is bounded like that. Then what it turns out that you can, if I can go back, we can modify the accept-reject algorithm as follows. We do sample y from the proposed distribution and u from the uniform distribution in 0 to 1, exactly as before. But the first test we do is if u is less than q star subscript L divided by m prime q star at the sample y. Alright? So we test if u is less or equal to this divided by that. If the answer is yes, then we return y and we accept this as a sample from the target distribution. If not, we do one more test and we check if u is less than pi star of y divided by m star of q star of y, exactly as we have done in our standard implementation of this algorithm. If this takes place, we accept y. If not, we repeat steps 1, 2, 3. Okay? So this modified algorithm, the way that you see it, it has this lower bound that you see here, all right? And there is, before the test that we did in the rejection algorithm, as we have seen this earlier in the lecture today, there is what is called the squeezing test that you see here, where we use this lower bound probability to evaluate if the sample is accepted or not. Actually, this is called the squeezing test, and this is called the rejection step, because effectively this is your last option. If this condition is not taking place, you reject, but if this condition is not taking place, you can still accept y if u is less than what you see on this term here. All right, so this is the envelope rejection method, and what we need to discuss is, can we actually find an automatic way to bound from below and from above, some reasonable distributions. And what I mean, some reasonable distributions here, I'm referring to distributions that they are log-concave. And here is the definition of log-concave. So if you take the log of pi, the second derivative has to be less than 0. So this is how the log of a target distribution would look like, right? So that's a concave distribution. So what we're going to do is we're going to try to bound this from below and above with a very simple scheme. So let's suppose that you have discretized this with these points x1, x2, x3, x4. So actually this will be samples that we will generate progressively, as you will see in the algorithm. And what I want you to is to concentrate, let's say, on a little interval between x2 and x3. Now, the lower bound of the actual, this is again the log, all right? This is the log of the target distribution. So I'm going to generate a lower and upper bound for the log of the target distribution. That would be my starting point, the log of the target distribution. So on this interval 2 to 3, I am going to take this straight line connecting this point and that point, so the points between x2 and x3, to be the lower bound of the log of the target distribution. And as an upper bound, I am going to actually take the minimum value of this straight line connecting this point x1 with the point x2, and of this straight line connecting the points x3 with x4. And you can see, for example, if you concentrate in this interval, the values of this line are less than the value of that line. So this is what I will take as the upper bound, and in this region, this is what I will take as the upper bound. I give you the equations if you want to study this, but literally what I have said is the lower bound for the log target distribution is the straight line that connects this point with that point. This is what I have here, and the upper bound is the minimum of this line and that line, which is what you see in these equations. Okay? Of course, because you're going to progressively generate more and more samples to implement this algorithm, you're going to have to set a lower and upper bound to the left of your sample points and to the right of your sample points. And you can do this. You can set, for example, the lower bound to be minus infinity, and you can set the upper bound to be the zero of the line that connects the point 0 with 1 and the line that connects n with n plus 1. I'm assuming here that I have a total of n plus 1 points. So f here is the anormalized part of my target distribution. And again, apologies for the changing the notation again. I am trying to be consistent with the original references that introduce these envelope methods. So f is the normalized target. So log of f is now bounded, right? Is bounded from below by this function at h with underbar, and is bounded from above with this line h with overbar. And I put a subscript n to remind myself how many sample points I have. Now, if from this expression for the bounds of the log, you can actually derive bounds directly for the anormalized part of the target distribution. So f then is bounded from below with is greater or equal to this lower bound f subscript n, which is nothing else but e to the h underbar n, and similarly from above is bounded with f bar of n, which is nothing else but e to the h bar subscript of n. So f is bounded by f underline and f overbar, and I'm writing here this upper bound as being some constant, some normalization constant, times some distribution that is easy to sample from. This is not very much different, having a proposal distribution that is known up to a normalized constant, but you sample from that proposal distribution. This is what I have here. I have this upper bound written as some normalization constant times some density from which it is easy to sample from. So here's the algorithm. Literally, we're going to apply this envelope rejection algorithm where sequentially we will be sampling more points, and we will see if those points are accepted or rejected. So what you will do is you will start with some collection of points, and you can start literally with only one point. So this set Sn here is defined to include the points xi from I equal 0 to n plus 1. So if you start with n equal to 0 and s0, you start with 1 point. You sample from this proposal distribution Gn, and remember that's the distribution in your upper bound, exactly as we have done with the accept-reject algorithms. We're going to sample u from the uniform distribution 0 to 1, and then you do the squeezing test. You check if u is less than this f that defines the lower bound, okay, divided by, this is my upper bound. If this test passes, then we accept y. If this test fails, we have one more step before we reject. So we evaluate if u is less or equal to f of y divided by my upper bound. If that is the case, we accept, otherwise we reject, and we repeat the whole algorithm. So this automatic adaptive rejection sampling was introduced by Gilkes and Weil back in 1992, and it provides you for an automatic way to do rejection sampling, but you can guess that this is not an algorithm you're going to implement in high dimensions, because doing this enveloping in high dimensions is actually not going to be a nice and easy thing to do, if you can do it even at all. Okay, so this is really for distributions in one variable. Okay, and by the way, if I can go back here, so when you're already basically, so let's say that your last sample was accepted, you will have to update the set of the sample points as n, and this is what the last step does in this algorithm. So if y was accepted, you will enlarge Sn to include y, and then you keep repeating, repeating the algorithm. Let me show you where, for example, you can use this envelope adaptive rejection sampling algorithm. Let's say that you do some inference and you have some data x and y coming from some Poisson distribution. So that's my likelihood. Okay, let's put some prior on the parameters a and b that come in the Poisson model. So I'm going to put a Gaussian on a and a Gaussian on b as priors. So the posterior looks like this, just multiplying the anormalized likelihood with the anormalized priors. And if you take the logs of this, right, you can have the full conditional. And if you concentrate, actually, I'm sorry, you can have the full posterior of A and B. And if you look at the conditional distributions of A and B, just to make the calculations easy, you can easily derive the log of the conditional of A given B and the log of the conditional of B given A. And so, for example, if I look at the log, if I start with the joint posterior and I take logs and I only keep the terms that involve A, this is what you get, and this is effectively the anormalized log conditional of A given B. So you can take second derivatives of this and you can verify that this is a concave distribution because the second derivative comes to be less than 0. And you can do the same thing with the conditional of B. So effectively you can apply this adaptive rejection sampling algorithm because these conditional distributions, these conditional posteriors are log-concave densities. Okay, let me finish with another rather esoteric algorithm to show you that you can apply rather complex algorithms in sampling in rather complex distributions. So let's suppose that we want to sample from a CDF that is given by the form that you see on this slide. Okay, so I want to sample from this CDF F that is defined as the ratio of H evaluated at minus g of x divided by H minus 1, and G is a given simple CDF. All right, so ideally I would like to develop an algorithm that will be sampling from the CDF capital F, but through the CDF g of x, because g of x it's a simpler given CDF. And what is H? H is this polynomial of the form an xn from n equal 1 to infinity, and I'm using here the constraint that a1 equal to 1 and all the coefficients are taken to be greater or equal to 0. So that's, this weird problem. We want to be able to sample from a CDF that is defined by this ratio of these polynomials evaluated at minus g and evaluated at minus 1. Okay. So let me give you an example on where this may come from. Let's say that the CDF that I want to sample looks like this. All right, so this is f of x 1 minus cosine of pi x over 2, and is given by the ratio, as you can see, this series expansion on the top, and you can recognize, by the way, immediately the function g of x being x squared, right? and then you can identify from the rest of the terms what the these coefficients are in the polynomial a of x. Okay, so this is I want to sample from this. Okay, now by the way, if you ask, okay, that maybe you can see this expansion here, but you can say, well, but I don't see how is this related to 1 minus cosine of pi x over 2. Well, let me show you a very simple derivation. If you use a Taylor series expansion of cosine of x, all right, and you apply this formula, this Taylor series, this series expansion, you apply it to cosine of pi x over 2, you're going to get 1 minus this series. The term in the series I is 0, and the 1 cancel out, so this series expansion of 1 minus cosine of pi x over 2 can be written like that. And if you modify the exponents on pi and 2 to subtract minus 2 from here and minus 3 from there, and putting pi square over 8 to minus 1 on the denominator so that you get this expansion, what you get is you get 1 minus cosine of pi x over 2 being this series expansion divided by this term. Now, if you notice for x equal to 1, the cosine of pi over 2 is 0, so this is 1. So effectively pi square over 8 inverse better be equal to the numerator for x equal to 1. So that's what I have done here. I took the numerator, I reproduce it on the denominator by using x equal to 1, and now I have 1 minus cosine of pi x over 2 being the ratio of these two series, and that's the equation on the top. Okay, so again, so that we are sure that we understand what the problem is, we want to sample from this CDF, right, where h is given by this polynomial with positive coefficients and a1 equal to 1, and g of x is some simple CDF function. In our particular example before, g of x was x squared. Okay, so this is what we had in our particular example. Now, this looks very difficult now. I mean, how do we actually come up with an algorithm that will allow us to sample from this complicated CDF? Okay, so here is the algorithm. All right, so let's philosophize on this algorithm, and then I'm going to come back and I'm going to give you a proof that this algorithm actually will produce samples for you, that there are samples coming from the target distribution that is defined by the CDF capital of F. So the algorithm says generate a sample x from G, and remember G is a simple CDF, and set k equal to 1. And then there is an internal loop that says generate samples u from the same simple CDF G. Pay attention here, do not confuse this sample u with samples from the uniform distribution that we have seen before. So you sample u from the same distribution G, that's our simple CDF, and then you sample v from the uniform distribution from 0 to 1. And then you test if u is less or equal to x, and you test if v, that sample from the uniform distribution, is less or equal to ak plus 1 divided by ak. If those two tests are valid, then you update k, all right? If that's not the case, you stop. Now, if you update k, you come back to the internal loop, and you sample again another u and another v, and you continue, you increase the counter on k, or you stop. And if you stop, two things are going to happen. Either k is going to be an odd number, and in that case, you're going to accept capital X, which means that capital X is going to be a sample from the CDF, the target CDF, or if k is even, you're going to come up to the outer loop, and you're going to repeat the whole algorithm again. So you notice we have an outer loop, right? An outer loop that starts first with sample x, and then we have an inner loop that samples a sequence of u's and doing two tests if u is less or equal to x and v is less or equal to alpha k plus 1 divided by alpha k. And the algorithm succeeds when it gets out of the inner loop and k is an odd number. Certainly I agree that this sounds a very weird algorithm, all right? So the primitive form of this algorithm is known as the von Neumann accept-reject algorithm, and Monahan extended this to what you see in this slide. So what I have now, I have the difficult task of showing you with very few steps that actually if k is odd, that x is a sample from the true target CDF. So let's prove that. So to prove it, we're going to define the following event, an, that is x equal the maximum of x u1, u2, un, and I remind you, all of this have been sampled from the CDF g of x, okay? So all of these are samples from the same distribution. So I define an, the event x to be the maximum of this, and then I define at the same time this indicator function z1, z2, zn to be equal to 1, where z1, z2, zn are basically the indicator functions that basically test what I had shown you in the earlier slide, if v is less or equal to ak plus 1 over k. So if v is less or equal to ak plus 1 over ak, then these indicator functions are 1, otherwise they are 0. So basically the event that I have defined here is that I reach basically the end step of the internal loop. This test has passed all times, all right? So basically v at all internal loop tests was less or equal to ak plus 1 divided by ak, and x is the maximum of x, u1, u2, un. Okay. So now you wonder, how do we use this event an to prove that actually when we get out of the inner loop and k is odd, then that x corresponds to a valid sample from the target distribution. So let's first prove the following, that the probability of the joint probability of capital X being less or equal to little x and an is given by an times g to a power n. Okay, now you may have forgotten about this, but I mentioned in the earlier lecture how to compute the CDF of a random variable that is the maximum of IID random variables coming from the same distribution. And I remind you the CDF of this random variable that is the max of those is nothing else but g of x to the power n. So the probability that x is less or equal to x literally is g of x to the power n, okay? Because all of these are IID and all of them come from the CDF G. Now I also need to have, this is a joint distribution with the event an that requires, right, that requires that these indicator functions are all equal to 1, okay? So what does it mean, let's say that, so the first time I'm going to start, by the way, you are going to do the test and you're going to check A2, you are going to sample V from a uniform distribution, and you're going to test if V is less or equal than A2 over A1, okay? And this is going to be equal to 1 with probability A2 over A1. All right? So, so this is exactly what I have here. And the fact that I have gone all the way up to AN, this is what this event is all about, means that I am going to pass this test as well, and V is going to be less or equal than AN divided by AN minus 1. Now you notice, so this is the joint probability of capital X being less than little x and AN, and there's a lot of cancellations. This A2 here will cancel with the A2 appearing on the third term. A1 actually is equal to 1 in our setting of our problem. A1 cancels out also, and what I get is AN g of x to a power n. So the joint probability of capital X being less or equal to x and of the event AN is AN g of x to a power n. Now, there is one more statement that I need that is not very difficult to prove. If you look at the event AN, you can immediately see that AN plus 1 is a subset of AN. Because, you know, what happens on the next step, right? Things, you know, maybe you accept, or, you know, maybe this test here passes or not. So AN plus 1 is a subset of AN, okay? And why is this important? Because I can write the joint probability of capital X being less than little x with AN and the complement of AN plus 1 as the probability, the joint probability of X being less or equal to little x, comma AN, minus the probability that capital X is less than little x and AN plus 1. Okay, so if you think here, right, this is again the joint probability of capital X less than equal to x and AN complement. So effectively, you know, what you are looking is, you are looking from this joint probability minus that to get this, because again, AN, if you draw a picture showing AN plus 1 being inside AN, all right, you will immediately see that this is equal to that. Now, why is that helpful? Because I already have an expression for both of these probabilities in terms of AN and g of x to the power n, and AN plus 1 g of x to n plus 1. Now, I gave you lots of equations, all right, and still we have not even come close yet to prove that if we get out of the inner loop and k is odd, then that x will be a sample from the target CDF. So let's continue to see how that is possible. So let's compute the probability that we will accept x. So if you go back to this equation, right, we want the probability that we will accept x, okay? Now, notice to accept x means I need to get out of the inner loop, which means I need to have an event AN, but not the event AN plus 1, right? So that way I get out of the loop. That's one thing. And the second thing I need to have, when I get out of the inner loop, I need to have n being an odd number. So here is what I can compute. The probability of accepting x is nothing else but the summation of AN minus 1 to the power n plus 1, which is minus my polynomial h evaluated at minus 1. And I know you say, where is that coming? I described to you that with words, and here is the idea. If you use the equation that we derived before, where x is less or equal to infinity, and you have the event an, but not the event an plus 1. So, you know, at step n, you got out of the loop, basically the internal loop. We prove that this is an g evaluated at infinity to the power n, minus an plus 1 g evaluated at infinity to the power n plus 1. So this is 1, and this is 1, because these are CDFs. So this is an minus an plus 1. And the probability of acceptance, you know what it is basically summing all of these probabilities for n being an odd number. So for n being 1, for n being 3, for n being 5, etc. So again, I need to get out of the loop, the internal loop, which means the event an has taken place, but not an plus 1. And when I get out of the loop, I need to be sure that n is odd. So this is the joint probability that x is less than infinity, and an is true, but not an plus 1. And then when I sum these contributions for n equal 1, 3, this is what I get. So that's the probability of acceptance. And now, you know what, I'm ready to finish and compute the CDF, basically prove to you that this return sample is a sample from the target CDF. So let me assume that x was returned, okay, and I want to compute the the probability that capital X is less or equal to little x. Literally, I want now to prove that this thing gives me nothing else but the CDF f that is my target CDF. Okay, so I am going to write this probability using the product rule as the probability of capital X less or equal to x, and x is returned over the probability of x being returned. The probability of x return I just evaluated, right, is minus h evaluated at minus 1, and then the probability that x is less or equal to x and x is being returned is the sum of these probabilities, these joint probabilities that I derived before, where I exited out of the loop, right, for n equal to 1 or n equal to 3 or n equal to 5, so an odd n, and when I exited, an was true, but an plus 1 was not true. And you remember we derived this probability, and it was given by what you see here. This is this joint probability when I exit at n equal 1, this is the joint probability when I exit at n equal 3, and when you put them together, by a miracle, you do actually get that this, the probability of capital X being less or equal to x when x is returned is given by this h of minus of g of x divided by h of minus 1, which is the target CDF of interest to this problem. So again, what is amazing here is, if I can go back, we postulated a very complicated algorithm, all right? That's the von Neumann algorithm, modified by Monahan, that somehow by sampling in sequence from G and performing evaluation tests that you see here, we are creating an algorithm that somehow by its structure allows us to sample directly from this complicated CDF. All right, so that's as much as I wanted to tell you about this Monahan's accept-reject algorithm, right? Obviously, you guys can generate your own algorithms, and remember, if you come up with an algorithm and you make the claim that it actually gives you samples from some target distribution, you have no choice but somehow to do a formal proof of that. Algorithms required proofs, and this is what we have done with these little examples that you have seen in the lecture today. So let me finish here. This has been, I know, a more mathematical lecture than normal, so I'm going to finish at this point, and we'll continue in a few days. Bye.